Hello friends, welcome to our channel. Let's have a look at today's daily challenge problem. Problem 2375. Construct smallest number from di string. In this video, we are going to solve this problem by using Kahn's algorithm. So here, let me here Kahn's algorithm for topological sorting. So here, but we also need to use some heap data structure. So I would say this problem is a very nice problem. So we can use data, we need to use certain data structure, and also we can use Kahn's algorithm. So this is the natural suit for topological sorting for this problem. But in order to do the assignment of values due to the order relation, right, lexicographically smallest possible string, we are going to introduce heap to help us. So this is only one way of solving this problem. So actually, these several days, I guess the problems are related to backtracking. So you can also solve this problem by backtracking. But here, our focus is Kahn's algorithm plus heap. So here we are going to use min heap. So with that said, let's quickly look at the problem requirement, and then we'll explain how to make a connection of the topological sorting and the heap with the requirements in this problem. So basically here we are given a zero indexed string called pattern of length n. So this pattern string contains consists of two characters, I and d. So I means increasing and d means decreasing. So as specified by the last two bullet items. So we want to return lexicographically smallest possible string num that meets the condition. So actually, so here, because the digits are from 1 to 9, so their string order and their numerical order actually coincide. So we just need to start from the smaller number and then begin onwards. So however, if you look at example 1, so for example, the first three position has 3 characters I, so you can write 1, 2, 3, but you cannot write 4 in the third in the fourth one, because the fourth at index 3 the letter is D. If you write 4, and you have something like this. So you have if you write 1, 2, 3, and for index 4, if you write 4, then you are going to decrease. If you decrease, you will always have one of 3 to 1. So this is impossible, right? So that's actually the place we need to use heap when we do assignment. But actually, if we have I, so means that so from index I to index I plus 1, so it's going to increase. And if you have D, it means that from index I to index I minus 1 is decreasing. So we're going to think of like this. So we're going to think of this, if it's I, capital I, we regard the index I as a prerequisite for index I plus 1. And if it's a D at index I, so we are going to interpret that I plus 1 is a prerequisite of I. You can write like this, right? Meaning that at index I, if we have I and D, right? So this is the relation. So this way we established the graph relation, right? And then the smallest lexicographically smallest. So this actually introduced the heap. When we do the assignment, we need to start from small to less. So here, let me write it. So this is the first one, and this is the second one. So if you realize these 2 points, I guess doing the coding should be a straightforward thing if you know Kahn's algorithm and you know some properties of min heap. Now let me carry out this program, and then in between we are going to make some explanations. So first I'm going to initialize a graph, so we can use a adjacency list. So here I'm going to use collections default dict. So here I'm going to use a set, right? So basically you have a node and the set of neighbors, right? So that's what we want to. Also in Kahn's algorithm, we have a thing called in degree. I'm also going to use collections default dict. So here I'm going to map everything to be 0, right? So, and then let's first iterate over the pattern, right? So for this, actually we can introduce, and let me introduce like pattern plus 1. So this n will be our final result length, right? So now let me establish the graph relation, right? So for I, we enumerate pattern, right? So we want to distinguish the v is capital I or capital D. If v equals capital I, meaning that from this line, right, from I to I plus 1 increasing, so we regard I as a prerequisite of I plus 1. In other words, if you assign I some number, then if you want to assign I plus 1 some number, this latter number should be larger. So what we do is like an adjacent list at index I is going to add, right, I plus 1. So similarly, because there means that there's an edge from I to I plus 1. So the in degree of I plus 1 is incremented. So in degree of I plus 1 is incremented by 1. So this is the one thing. Otherwise, so V must be a capital D. It means that from I to I plus 1 is decreasing. So meaning this, right? So meaning that the adjacency list of I plus 1, so we're going to add I. And because there is an incoming edge from I plus 1 to I, so we're going to do in degree, so I incremented by 1. So this way, basically, you will have the relation. So in order to better understand this procedure, let me do some print, right? Print the adjacency list. And also, I'm going to print the in degree. So let's see what we have. Right, so here from this one, you can see 0 points to 1, and 1 points to 2, and 2 points to 3. But then if you look at index 3, so from 3 to 4 is decreasing. So we have an edge from 4 to 3. So 3 is in the neighbor of 4, right? And then if you look at I at index, this is 0, 1, 2, 3, 4. So because it's increasing, so from 4 to 5, there's an edge. So 5 is in the neighbor of 4. That's this key value pairs, right? So also you can see the nodes with in degree 0. Those do not appear in this print is the nodes with in degree 0 because of our initialization, right? Lambda equals this maps everything to be 0. So now let me comment this. So this one actually establish the graph relation. So what we want to do next is to do assignment. So because of this the requirements, we need to do this. We need assign a smaller index first. Smaller index first. Which smaller indices? Indices. Those with in degree 0, right? So that's the logic. So that's this one introduced the Kahn's algorithm. This one introduces the min heap. So now let's carry out that. So let's have a container. So here I'm using Q. Then for I in range m, right? So then if the in degree of I equals 0, right? Then we are going to push. I'm going to use this heap. So we are going to push this one, heap Q, heap push this index into the heap. So this way, each time we do the heap operation, we always have the smallest index. Then for the smallest index, we want to assign smaller value, right? So that's actually the logic. So now what we are going to do, so we are going to initialize a result variable that's for in range, so m, right? So what we want to do is that, let's see, we start from the smallest digit, that is 1, right? And then what we're going to do is the standard while loop, while heap. What we want to do, so we have the node, right? It's going to be heap Q, heap pop. We pop from this heap. So we can look at the current node. So as long as the node is in the heap, its in degree is in a state 0. Therefore, we are going to assign result node to be the current digit. So once we do an assignment, so we are going to increment the digit, right? And then what we are going to do is to check the neighbors. And then if we want to update the in degree dictionary, so for neighbor in graph, right, node. So what we want to do is the in degree of this neighbor is decremented by 1 because we deleted this node, right? This node, and there is an edge from node to neighbor, right? Because this node is deleted or is assigned, right? So this in degree is decremented by 1. So then if the in degree of this neighbor is 0 now, then we can put it into the heap push, heap and neighbor. And this way, after we finish this while loop, so we're going to assign all the positions here with the right digits. So now let me just return this. So we can first print this result, right? So here heap is not defined. So let me heap Q, heap pop, so let's see, where is the problem? Heap. I guess HQ, yes. So let me. Is there some typing problem? Let me see. HQ, right? So I'm using. So now let's see. Similarly, we need to change the other heap. Let me change this to be heap. This is my convention, so that may be better. Yeah, so you will have this one, right? So this is exactly the one they return. So what we want to do is to prepare the return and give the format. So here we can use list comprehension, right? So we can join all those. So here we can make everything to be a string, digit for digit in result. So let's see. Yeah, it passes the two test cases. Now let's look at the generic case. Yeah, it passes all the cases. It's actually very fast this way. So before we end this video, let me give a quick summary. So here we solve this problem using Kahn's algorithm and min heap. So the Kahn's algorithm is due to the graph relation, or induced from the pattern string. So this is one thing. And this actually establishes a natural relation of the requirement increasing or decreasing with the topological sorting. And the second one, when we do the assignment, we want to return the lexicographically smallest possible string. So this actually motivates us to introduce min heap. This way we can do Kahn's algorithm, and in the process we do assignment. So because of the heap property, each time we assign with the currently smallest digits. And again, due to the fact that the numbers involved are only 1 to 9, so they are string order, right? So because let's say 1 is less than 2, and they are integer order. So actually these two orders coincide. That's why we can do coding like this. So if you inspect this code actually, or if you can search some of applications of Kahn's algorithm, like let me still remember some example. Kahn's algorithm, you can practice like in cost scheduling, right? So some problems in leetcode involves cost scheduling. You can use Kahn's algorithm. With that said, I guess that's it. Maybe in a future video, I'm also going to explain how to solve this problem using backtracking. So thank you for watching.